Hello, everyone. Welcome to the Robotics Colloquium. We meet most Fridays, and we're super excited to have Matt Barnes. Matt is a former member of the Personal Robotics Lab. Matt and I met when he was doing his PhD at Carnegie Mellon University, doing some really fantastic work in machine learning. And we met as runners. We both have been gone through the process and pain of running at long distances together and talking about math as we were running. And then Matt moved over here to UW and did his postdoc with me. Again, did some really interesting work, particularly around imitation learning and reinforcement learning, and thinking through how we can use very low dimensional data like e-stops to figure out how we can train robots. After that, Matt moved over to Google and has been working there since. I've really enjoyed all my interactions with Matt. I think Matt is a very strong theorist, but also incredible implementer. And I've always enjoyed the insight he's been able to provide through his work. I think I find his algorithms to be not just incredibly useful and practical, but also very elegant. So really looking forward to some of the new work that he'll talk about.
Thanks, Sid. Very kind words. So like Sid said, I'm Matt from Google Research. And today I want to talk to you all about how we took inverse RL from what has historically mostly been very small scale laboratory experiments to planetary size MDPs with hundreds of millions of states and billions of users. So this was actually a project that I had wanted to work on for a long time, and I went to Google and tried to get this started, and we worked on it for several years. And so this is kind of, I have the benefit of hindsight now, looking back on this project and what we learned. And some of the work that I did with Sid here, too, is featured in this. So we built upon that, too. So I'll share a lot of the practical, very real-world lessons that we learned. Yeah, we had a great team at Google across research and DeepMind and Maps, people that had a lot of really strong ML background and a lot of really strong engineers that understood the data in Maps and had, a decade of experience working on routing Maps from the baseline production system, and then how could we take ML and actually improve that. So it's great to actually be here at UW surrounded by roboticists because A, you already know so much about inverse RL. A lot of this work came out of the robotics community trying to learn for helicopter control, for taxi cab route finding, for pedestrian forecasting. So the history of inverse RL goes back, multiple decades. There's this great photo of Andrew Ng and Peter Beal and Adam Coates at Stanford in the mid-2000s with their helicopters, and they were doing imitation learning in inverse RL. And then also, like Sid mentioned, I did my PhD in robotics and did a postdoc here, so it's actually good to be home and to be back here. So this is a great opportunity. So I'm going to route optimization in maps is a pretty classic inverse RL problem. Where you have a discrete deterministic MDP, where your states are all the road segments in the graph. The actions represent valid turns that you can take at certain intersections. And then your demonstration trajectories actually come from some real set of users. So in this case, these are actual Google Maps users' trips when they're navigating in the real world. So this MDP is undiscounted. It has an infinite horizon. And then the destination state is a self-absorbing zero-reward terminal state. So this is where you're trying to actually reach when you're making a navigation request. This is actually kind of similar to the language modeling setup in some ways, where you have an end-of-sentence token, and that's analogous to the destination. So there are a huge number of factors that go into choosing what the best route is in Google Maps. I can't talk too much about it, but to shed a little bit of light, this includes obviously the ETA. It includes the complexity or directness of the route. It includes the road surface condition, U-turns, border crossings, and many more different factors. Now, ETA obviously is a very machine learning-based system, but how the rest of these factors get incorporated into choosing the best route is a surprisingly manual process with all different kinds of cost penalties on crossing certain borders or certain types of U-turn maneuvers, different type of road surface conditions. And it's amazing how well this system has worked at least for driving in many countries. But talking to a bunch of people with a strong ML background, it's not surprising that a very manual system scales poorly geographically, it scales poorly across time, and it scales poorly across different groups of users who have different preferences. right? So taking an ML base to this of trying to actually think, actually, what do people care about? Let's not manually tune these penalties is going to hopefully get us much higher performance. And then the other thing too, and actually this is how I got into this project, was that if you think about modes like walking and cycling, where ETA is actually only is a much smaller factor than it is for driving. People really care about safety. They care about the comfort or the condition of the road that they're on. These are much greater factors, and those factors are really hard to measure versus ETA. Like ETA is very easy to measure how long it took someone to get there. Can we predict it? Safety is much less tangible. It's much harder to quantify. And so if we want to be able to give the best routes for walking and cycling, we really do need to learn from people's actual behavior in the real world. So the bird's eye view of today's talk is that there are going to be 3 sections. So first, I'm going to give a brief recap of inverse RL so that we're all on the same technical page. I'll also provide a couple different intuitive ways to think about this problem that I think hopefully will help you, going forward when you think about what is inverse RL, what is the problem, and I think we'll also shed a light on a few of our contributions today to how we arrived at different algorithms. Then second, I'm going to address the primary technical challenge that we face, which is how do you scale these algorithms to really, really massive MDPs? These graphs are an orders of magnitude larger than the previous inverse RL benchmarks, at least to the best of our knowledge. And then finally, the last part is here is kind of like, with hindsight, what did we learn over these couple of years about how do you actually get these algorithms working in practice? What are some of the real world lessons that we learned that are, maybe a little bit about specific algorithms, but more so about just like how do you try to solve problems like this in the real world? And I hope that that will also be useful for you in your future. So inverse RL fundamentals. So in imitation learning and inverse RL, we're given an MDP, excluding the reward function, and then we're given the set of demonstration trajectories that I already talked about. And we don't be able to replicate those demonstration trajectories. So this is typically formulated as a divergence minimization problem, where we're trying to minimize the divergence between these experts' demonstrations and then our policies demonstrations. And here when I say policy, I mean, if we're learning a reward function, the policy that's induced by, the optimal policy that's induced by that reward function. And we looked at this problem actually quite a bit when I was here at UW. We had a really nice paper with Sanjuban and Kay, too, was on that as well. So it was some great work there. Now, if you take this F divergence objective and then you follow the standard GAN derivation, you can reformulate it as this two-player game between a discriminator. And so you can think about the discriminator here is your reward function, and then you have a generator, and this is your policy. So what makes inverse RL so expensive is that this inner minimization that's happening, this is actually an RL subroutine, right? For the current reward function, compute the optimal policy. That's the RL problem. And then the outer maximization, that's where you actually update reward function based on the trajectory rollouts from the policy. So this is a very general formulation of the problem so far. Now, maxent, which I'm going to talk a lot about today because I think it's a very classic algorithm and an easy way to understand a lot of other methods, takes us one step further, and it just adds this entropy regularizer on the policy. So this is this H term here. So the same min-max problem, but with an entropy regularizer and then some regularizer on the reward. And now with this regularizer, you can show that the optimal policy satisfies a softmax distribution over trajectories. So these are like, in the routing setting, this is all the possible paths between the origin and the destination. Now, actually computing this softmax here, this second equation, directly, unlike a lot of other classification problems, is intractable because there are an infinite number of possible paths that you can take between an origin and destination. But I think that this view of the problem provides some really helpful intuition because you can think about this as, like I said, like as an infinite classification problem that we're trying to just learn this classifier, which is the policy. But really the challenge is like, how do you compute this loss? How do you optimize it? And this is where a lot of your classic methods like dynamic programming or using some type of path planner come into play to actually be able to optimize this objective function. So just for the purpose of this talk, I quickly created like what a visualization of maxent looks like in this like very simple like 15 by 15 or 10 by 10 grid world. So on the left, you can see this is the inner minimization step. So this is for some given current reward function, we want to compute the partition function, which is what defines the policy across our entire state space. And you can actually see how information at this part of it is flowing backwards from the destination across the rest of your MDP. And then on the right, you can see the rollout of that policy. Once we've actually computed this policy from the partition function, we roll out that policy across the entire MDP until it's reached the destination. And then that gives us our stationary distribution. OK, so on the left here, this is our demonstration trajectory, right? So this is just one path between the origin and the destination. And on the right here, we have, this is our policy distribution. So this is the rollout that we did on the previous slide. And now what happens is that you want to try to increase the reward on states along the demonstration trajectory that were undervalued by the policy distribution. And then you want to decrease the reward on parts of the policy distribution that are not part of the demonstration trajectory. So obviously, this is going to have really high variance right now because it's just a single demonstration. But you can imagine, if you have many of these, then you'll actually get a much lower variance gradient. Yeah, so the overall process of this kind of looks like, right, you estimate the policy given the reward, you update the reward to better reflect the demonstration trajectories, and then you repeat this process. So this is the basic max-end IRL algorithm. And if you understand this method, then I think it's typically just like 1 or 2 more steps to understand other types of related methods that are out there. This is really one of the most classic ones. So for example, another well-known one that's pretty old too is Bayesian IRL. So you remember that the maxent, I said, policy satisfies the soft max distribution over all trajectories. So BRL makes a slightly different assumption, which is that you assume that the policy is you have a probabilistic policy with a soft max distribution over these Q star values, where these Q star values are the cost of the shortest path to the destination. So you can think about Q star as basically just you call Dijkstra or A star in your graph, you get the shortest cost path, and then your policy is a soft max distribution over these. So this is how it becomes probabilistic. And then you just want to, then you'd run the maximum likelihood estimation on this policy. Or another one, max margin planning or LRCH is the more modern version of it, assumes a margin loss. You can think about, this is basically the SVM version of inverse RL. And so you have a margin loss that attempts to make the expert demonstration trajectory better than all other trajectories by some type of margin. So this method, it really lacks robustness to noise and is rarely used in practice, pretty similar to how SVM is rarely used in practice nowadays too. But it does have one really nice property, which is that we're able to really efficiently compute this loss because all it requires is running Dijkstra in the graph to compute this margin augmented shortest path. So it's super efficient, and we're going to come back to that later because we want to think about how do we get the benefits of this and also get some of the robustness of the stochastic policy in maxent. So I'm going to actually skip over this. This is basically a table that summarizes all the different methods, and we can come back to this later if there are questions about it, the different pros and cons, but probably more of a reference more than anything else. Yeah, go ahead.
Sorry, quick question. The notation that you had for the F divergence one, does it assume like reward is linear in features, or is?
Typically not, no. But yeah, one of the baselines I'm going to show later does use a linear reward function. But yeah, you can assume any type of, I think most of the theoretical guarantees sometimes will require that type of linearity, but in practice, no, you can make it nonlinear. Yeah. So that's the fundamentals. So now this is the second part of the talk where I'm going to actually address the main technical challenge that we face, which is how do you scale these types of methods, which are typically very expensive, to very large MDPs, like out of the laboratory setting and into the real world. And we wanted to do this for the Google Maps problem, obviously. So if you look at the worldwide road network, it contains several hundred million states and a similar number of demonstration trajectories. And we'd actually had access to tens of billions of additional demonstrations if we had needed them, but this was basically all that we needed for this problem. We were able to get by with this. So given this very large MDP and demonstrations, remember that our goal is to try to recover the latent reward function across the graph and then use that to serve better routes. So we had to introduce quite a few different scalability tricks to actually get this working in practice. I'll give a high-level overview of kind of a couple of different pieces right now, and then I'm going to actually dive into 2 of the main algorithms that we came up with later that will take advantage of some of the insights that I talked about. So one engineering thing that we had to do was we used graph compression. So this is like you can think about the graph is represented as this padded dense tensor in memory, where every row of this tensor is a state and every column of this tensor is an action. But because a very small number of states have a very large number of possible actions from them, so this is like, most road segments you think about have like 2 or 3 or 4 turns that you can take at an intersection, but there's a small number that just have a huge number at these very complicated intersections at like ferry terminals, for example, or in some parking lots. So there ends up being quite a bit of padding in this tensor. And we came up with a few different tricks that involved essentially like inserting or merging nodes in this graph that allowed us to significantly reduce the amount of padding in this tensor. And these types of graph compression and decompression on the other side provided nearly a 3x speed up in the training times of these methods. Not going to go too much into it now. The nice thing about these is that they're completely agnostic to what algorithm you're running. So you can think about this is just a pre and post processing step on your data set. And then you can run any method you want to on top of it. So second, we took the global MDP, and then we sharded it by metropolitan region. So this is we had about 250 shards across the entire world. And then we learned an expert for each of these individual shards. So this step was necessary to make the problem even remotely tractable. I would say we couldn't actually run the worldwide problem without this step. And you can think about basically that we can craft the reward function to share any information across these shards that we want to. In practice, we had enough data that we were actually able to pretty much learn just one expert per geographic region with very little information sharing. But if you had less data, we could have shared more information across these local experts for each of the metropolitan regions.
So those experts end up being like a model of how people drive in that place?
Yeah. And we even have some
interesting variations.
We do. I don't know if I put them in the slides, but there is some graph in the paper where we basically looked at we looked at the generalization error across. Like if we took a model that was trained in like Syracuse and then we tried to deploy it in Los Angeles, like what would the drop in performance be where if we took the Los Angeles model and deployed it there? So we did that cross-city generalization, and there's like a very clear drop in performance across the diagonal from that. I'll try to pull it up later if I can.
A quick clarification. So just so I understand, do these shards have any intersection?
Yeah, so there are some parameters that are shared across them.
Okay.
Some of the parameters are shared.
I see. And then their union is the worldwide road network?
Yeah.
Okay, so you cover everything and then you shard it. And
yeah. So there's no geographic overlap between them, but there can be parameters that are shared across their world models themselves.
Geographic overlap.
Yeah.
And was there art to sharding, or will you talk about that?
We tried to, there was some art to it. We tried to minimize how many paths were crossing shards, because then we couldn't really train on paths that were crossing these shards. So we generally focused them around a large metropolitan region, so like the entire New York area, which include like Philadelphia, New York, and like a large area around there. And that allowed us to have very few tracks that would cross the metropolitan regions. Yeah, and so there were already like some predefined regions, and we just basically used those for the shards definitions. But yeah, there was definitely a challenge thinking about. I mean, it's nice for this problem because it is so like everything's clustered naturally in the real world. Okay, and then lastly, and this is the part that I'm going to jump into more, is that we introduced 2 new inverse RL algorithms called Maxent++, and then Receding Horizon Inverse Planning, or RHIP. And these are probably the most technically interesting discoveries that we made, and so I'll spend some time talking about them. So first, Maxent++, you can think about this provides strict improvements on the initialization conditions of Maxent that in turn improves the training times. The name itself is a nod to k-means, k-means++, if you're familiar with it. You can think about like that's improved initialization conditions on k-means. This is a similar type of improvement on top of Maxent. So to arrive at Maxent, you first have to realize that the backward pass dynamic programming in Maxent is actually performing power iteration. So this is the exact same algorithm that's used in PageRank. And in our case, what Maxent is actually doing in the backward pass is that you're computing the dominant eigenvector of this sparse exponential reward adjacency matrix here called A. And so this in itself, I think, is something that I had not really thought about too much when I was reading around Maxent originally. It's not in the original paper. It is a little bit in Brian Zewart's thesis at some point. But think about this as like what we're actually trying to do in the backward pass is to compute the dominant eigenvector of this graph. And that Maxent is using power iteration to do that. So this means that this visualization on the right that I showed earlier is actually showing the convergence of power iteration. So it begins with initial guess at z. That's when it starts. It starts with a one-hot vector at the destination. And it keeps performing this matrix operation on z until it converges. And Maxent chooses this z to be a one-hot vector at the destination, like I said, which makes sense if you're thinking about the problem in a traditional sense. But if you start thinking about it a little more abstractly, in like a pure mathematical sense, this choice of z is maybe not the best idea, because it's actually very far from your final solution that you want to get to. And this requires a lot of iterates to get this to converge. So the question is, like, what would be a better choice at an initial z to quickly compute this dominant eigenvector? It turns out that actually, if you choose z to be just the shortest cost path to the destination from every state, we can actually prove that this is strictly closer to the final solution, to the true dominant eigenvector of the graph, than the one-hot vector. So the left thing, that's what Maxent typically uses. Very cheap to compute, right? It's just a one-hot vector. The right is the true solution that we're trying to get. And if we just plug in this shortest cost path to the destination as our initial z, this is strictly closer, and it allows us to use fewer iterates of power iteration in order to converge. So when we take the trick and plug it into the entire end-to-end system, it provides a nice little speed up in training times, about 16%. And it's also like a no-brainer, because you basically have to add 3 lines of code to call Dijkstra, and you get this improvement in training speed with no drop in any of your other metrics. So this is basically, I think, a nice improvement on Maxent that really is, it's a free lunch, right? You don't have to pay anything for this. As soon as we started thinking about this as power iteration, this led us down this other rich path of other types of eigenvalue solvers. People in the math community actually don't really use power iteration that much. They use something else called Arnoldi iteration, which, it's much more complex, but it is much faster on most types of problems. However, a very unique aspect of the inverse RL problem is that we actually care about the error of the solution in the log space, because we actually use this partition value in a softmax function at the end. And typically, people look at error in the linear space. And so when we implemented power iteration in Maxent, we actually did it in a log. We created a log space version of power iteration to compute this to make it numerically stable. And there is not, at least to the best of our knowledge, any way to do this with something like Arnoldi iteration. And we certainly tried to do that. So you can see here that even on very small MDPs, Arnoldi iteration becomes numerically unstable even around like 40 states. So this is on trivially small graphs. It becomes a problem. And if you visually inspect what's happening here, so I should have put some better labels on this. So the left column is power iteration. Right column is Arnoldi iteration. At the top, you can see the solution in the linear space, and then the solution in the log space on the bottom. So you can see how things are pretty boring in the linear space up here, right? Everything's pretty close to 0. You really don't start to see signal when you look in the log space here. And log power iteration does a really good job of this, versus Arnoldi iteration gives you lots of invalid values, and isn't able to solve for these values very close to 0, because it's doing it in linear space instead of log space. I think that this would actually make for some very interesting future work if someone wanted to try to figure out how to do these other solvers in log space. A pretty theoretical, math-focused type of research, but it would be interesting. So the second algorithm I'm going to discuss today is called RHIP, or Receding Horizon Inverse Planning. From a bird's eye view, RHIP generalizes all the algorithms that I've talked about so far today, and actually allows interpolating between them via its choice of a planning horizon parameter. And this allows us to basically add another dimension to our hyperparameter optimization, where we can find even better policies that we couldn't have realized before. The key inside of RHIP is that if you look at existing algorithms, there's often this trade-off between the use of cheap deterministic planners, like an MMP, and robust, yet in stochastic policies, like in maxent. And the question is, can we get the benefits of both of these worlds? So what RHIP does is that we use the more expensive stochastic planner in regions close to the demonstration, and then we switch to the cheaper deterministic planner beyond some horizon. So on one extreme, by using a horizon of 0, RHIP reduces to MMP or lurch. And then by the other extreme, using a horizon of infinity, it just reduces to maxent. And then by adjusting this horizon, we can kind of interpolate between these algorithms and find a performance sweet spot. Now, originally when we began adjusting this horizon parameter, we had expected it to smoothly trade off between training time and accuracy, and they naturally create a Pareto curve. Surprisingly, we found that by tuning the horizon, we could actually learn policies that were both faster and slightly more performant than maxent. Like they actually strictly dominated maxent on this training time and accuracy curve. One possible explanation for why this could be happening is that we're learning from humans' actual behavior in the real world, and humans might plan similarly. Like this could actually just be to better specification with actual real-world behavior. Like humans may do some type of more expensive planning around their local horizon and then make approximations beyond that, and RHIP makes a similar assumption about the policy class. And so maybe this is actually just better reflecting humans' actual behavior in the real world. These improvements were pretty modest in terms of the actual accuracy, but I think it's still an interesting experiment. So overall, once you take all these things and plug them together, we get a policy that is a 16 to 24% improvement in route conformance for driving in two-wheelers, respectively, across the entire world in Google Maps. These numbers are compared to the actual production baseline that's running in Maps. So these numbers are a pretty massive improvement, but also one that I think is intuitively reasonable to expect, considering the handcrafted nature of the baseline. Couple questions there.
How do you measure improvement?
So we use this metric here is route conformance. So what we're looking at is like what percentage of our routes actually agree with the user actually took in the real world, right? So you can think about if user deviates from the route we suggested, then something bad would happen. Now, I'm going to talk a lot later about which routes we look at from users, because the filtering of those, like sometimes people will make mistakes versus they actually do something that they think is better. It's very important to try to distinguish between those two different things. But you think about in your data set, basically, what percentage of the routes are you agreeing with versus not? So you can think about it as like sequence level accuracy or trajectory level accuracy. Good question.
Yeah, just as an aside, this is actually quite relevant also for last mile drivers. I think of like Amazon drivers, and they've got their packages inside their black vans, and they get a plan, essentially like a Google Maps plan, saying go here, drop this package, go here, drop the next package, and on and on. And route conformance is actually a very important metric for that, right? Like they may say, I can just park here, and I can take these 4 packages, and I can run off and drop them off in all of these places. Or this route takes me through a school that is letting out all of its students, so I'm going to bypass this altogether and finish all of this other stuff away. So route conformance is like something that's very, very relevant, not just in the in our driving, but also in last mile stuff.
Maybe we'll cover this later, but do you have metrics baked into this which account for the fact that you're changing traffic as you're making these recommendations and getting people to conform to them more?
Yeah, so there's 2 different variations of this metric. There's both an offline one where we just take a static data set and we say, okay, if we take a policy, what percentage of the routes agree with this policy based on the static data set? And then there's also the online version of it, where we're actually let's take the policy and roll it out in the real world, and which percentage of routes actually agree with that policy in the online world. Now, there's obviously a bias towards the production system with the static data set, because people just have a tendency to agree with the natural route, right? And so it doesn't favor our approach in these offline numbers here. Yeah, does that make sense? Yeah. I'm not going to show any of the online numbers today, though, because I can't share those.
Do you have an interpretation for why some places like Kyoto you have this massive improvement?
That's a good question. I've been asked that before. I wish we had done more investigation on that. We did know a priori that there were some places that have worse quality than others. I was surprised by some of these numbers too. I wish I had a better answer to that. I think, so this project is already completed, so we probably can't go back and investigate that, unfortunately. But I would have liked to have done that, yeah.
So it's just interesting there's so much spread.
Yeah, there's probably some just like, I don't know, yeah, I'm not sure. Natural variance to it.
I guess like you talk about the relative numbers, but maybe I wonder if the absolute numbers were already good there or something?
Yeah, it's also like, I know like route quality in cities is a lot sometimes worse in like suburban areas where there's fewer route options for someone to even take. So like in places where there are just more options for routes, then the probability of getting the right route is lower to begin with. So I think density has a factor to it as well.
And one clarifying question.
Yeah.
I never thought that I could like not be conformant to Google Maps. So this is super useful to learn as a human being. I thought Google would be mad at me. But sometimes I click on the similar route. Is that considered route non-conformance or not?
Not the way that we set this up. I think you could definitely learn from that type of feedback too, but we're not learning from that. We're only learning from people's actual trip they took after they started the navigation. But that's another type of feedback that you could learn from, though, definitely.
But if the route non-conformance that I had could have been a similar route, like I'm thinking of a similar route as like, I don't know how you do it, but like there's not just one similar route, but there's probably like a set of similar routes, some of which you don't expose to me.
Yeah.
But if my non-conformance actually was one of those similar routes, do you discount that or do you account that also?
In our setting, the baseline we're comparing with is just what the best route was. Yeah. So if you selected a different route and then drove that different route, we would consider that, at least in these metrics for the paper, we would consider that non-conformant because we're comparing against a fixed baseline, which is just the production system, and that's only picking deterministically the best route.
Got it.
But I think there's other ways you could look at metrics that would be important to look at too. I think you should probably slice it that way too. Yeah.
Does the state space consider like the dynamic like things also like traffic, time, and?
Yeah, so I'll talk about the dynamic ETA aspect later. Yeah, so we do have, the features are changing over time. I'll talk about that later. That's an important thing.
One last clarification.
Yeah.
You showed all the improvements. Like, were there any places where it didn't improve or got worse? Is that the next slide?
Well, I don't know if I'll show this to you.
We're going to have a private conversation.
Yeah. Okay. So after finishing this project, we did have some time to reflect on it and kind of what the important lessons that we learned. So now with 2020 hindsight, I'm going to share some of those practical lessons. But we didn't know going into it, but I think were very helpful as we went along. So I hope that you'll find these particularly helpful. So the first one is obvious, but I want to show a case where very non-intuitive reason why this was helpful. Okay. So the first one is visualize your predictions. So we had this perplexing problem when we were training Maxent, where we'd often experience these huge loss spikes in the training curves. And these were seemingly at random intervals. We couldn't figure out like why this was happening. Like it was not a bug, and we could not figure out what the heck was happening with this policy. So when we visualized, what we actually did was we actually took the policy and we visualized its state distribution at the instant that these spikes would happen. So we said, okay, where is the policy in the forward pass? Like when you take this policy and roll it out, what is it doing in practice? So what we found out is that basically every single time when these spikes happens, the policy was getting stuck in these little tiny parking lots. So this is like this example in Syracuse, New York. And we already had constraints on the reward function. So we were guaranteed that the rewards were negative or costs were positive every place on the graph, except the destination, obviously. And when we thought, OK, if the costs are negative every place, the costs are positive, rewards are negative, then the policies should always converge. It turns out, though, there's actually a really strong theoretical reason for why this was happening, even in the linear reward function case. So this is not due to some weird thing about using a deep network or anything. This is actually a fundamental issue of Maxent. So to understand this phenomena, let's take our insight from earlier, that Maxent is an infinite class classification problem with a softmax distribution over this infinite set of trajectories between the origin and the destination. So there are two key counteracting properties that determine whether or not the transition, that characterize the transition between finite and infinite loss. And both of these properties are actually pretty obvious. So first, the number of possible paths between the origin of length n plus 1 is larger than the number of possible paths of length n, right? If you have longer and longer paths, there's more possible paths that you can take between origin and destination. Second, paths of length n plus 1 have, at least on average, higher cost than paths of length n. Also obvious. Longer paths, higher cost. OK, so the question is that as we start to consider longer and longer paths, the number of paths increases while the per path reward decreases. But will this overall partition value converge to a finite quantity? It turns out this happens only, obviously, when the former outweighs the latter. And the issue happens in parking lots in particular because this is regions of the graph that have a really high branching factor and where there's many short, low-cost segments. Essentially, you have a large number of these low-cost paths in the parking lot, and this is what blows up the partition value. And more precisely, we actually prove that this happens precisely when the dominant eigenvalue of this matrix A drops below 1. So this is a very precise condition when this happens. So we actually did this, and we proved it, and we were really proud of ourselves for doing this. And then I was reading through Brian Zebart's thesis from 15 years ago, and there's a footnote on page 130-something, and Brian's like, yeah, if the dominant eigenvalue drops below 1, then this will happen. And we're like, man, how did Brian Zebart know this so long ago? But it's interesting that we came about it from a very different perspective. We saw this happening in practice, and we were like, what's going on? Let's figure it out. But if you have never read Brian Zebart's thesis, it's really good. So definitely recommend doing that. After that, so the second lesson is that you're going to have to deal with poor quality data in the real world. Yeah.
The previous one?
So let me see if I go back. So there's a couple different things that you can do. We tried originally to actually come up with in the linear case even, we tried to come up with a project it back onto the convex set of allowed values. We weren't able to come up with a way to efficiently do that. We were able, you can think about it as basically in the linear case, you have a convex optimization problem, and you have this infinite loss defines the boundary of your convex set that you're optimizing over. And you don't want to leave this convex set. But sometimes it can be the optimal value can be really close to one of these boundaries, especially if you have really big reward functions. So we did some things careful initialization of the values, very low learning rates helped. The other thing too, though, is that you can also do early stopping in the backward pass. So if you just stop the backward pass early, then it won't blow up as much. Is part of it too. So there was a couple different tricks that we used. Also methods like BRL and MMP Lurch actually don't suffer from this, so it's only maxent. Yeah. Also, you'll notice on the graph that it wasn't, even if the spike happened, we were still able to get the loss to converge reasonably. So if it happened once in a while, it wasn't terrible, but we couldn't, there was never a way that we could figure out how to do it, how to prevent it entirely, I think, from happening. So you'd still have it occasionally leave the set.
So are the spikes always parking lots, or are there other?
We looked at a couple. We looked at a handful of examples, and they were all similar things like this. Yeah, for the most part.
It's another solution. You could just sort of
remove
have
the
a special
lots.
case for parking lots.
Yeah, just remove. Yeah, that's a good point too. Okay, so the second lesson is that you're going to have to deal with poor quality data in the real world. Data is just always messy. This is one of those unsexy problems, but it's super important to look at. I think people in the language modeling space are increasingly starting to appreciate this because investments in improving data quality often outweigh improvements on your actual model training or architecture. So we knew a priori going to the problem that actual errors in the base map features. So this is we have some information about the state of the world. Some of that state is incorrect. We might think a road's closed, it's actually open. We might think it's paved, it's actually a dirt road. We know that many of these things were causing bad routes and maps at the beginning. We already know this. People have been manually fixing this for a decade. And the question is, can we actually try to fix some of these errors by actually looking at users' demonstrations? So to address this, what we did is we introduced this very large 360 million parameter sparse reward model where there's one parameter for every single state action pair in the graph. And then you add a really high L1 penalty on top of this reward function. So this is just in addition to your base reward function, you add this sparse component to it. So after training, the majority of the parameters in the sparse model are going to be 0. Like your standard reward model of the features you have is going to capture most of the information. But the ones that do have non-sparse values that are really large, those tend to happen where there's some issue in the base map where our normal reward model wasn't able to explain users' behavior based on those types of features. So for example, if we have one of our UK shards, if we just took the largest sparse reward in this area, you get this road in Nottingham here. That corresponds to a road that's incorrectly marked as private due to the presence of this gate that you can see in that middle figure. But in practice, this gate is actually never closed. It's mostly just for historical or decorative. I don't know why it's there. Never actually closed in practice. Users just drive down this road all the time. But maps have been recommending this very long, narrow detour, this red route. So this one has this really old, narrow road. It was several times longer than the blue route. But by highlighting this road segment with inverse RL, then we're actually able to flag these to operators, and then an operator can go back and actually fix the underlying base map. Where we're basically like, here's a bunch of roads that users are doing the wrong thing, like based on our inverse RL. Like, can you fix this? So it's a nice way to kind of close the loop from user demonstration in a very principled way to how to actually use inverse RL to highlight data quality errors in the underlying base map. And then the wins from dealing with poor data quality were not just qualitative examples. These led to very significant gains across all of our models. So these gains actually do exceed the gains that we saw by making improvements to the algorithm itself. So this bump from blue to red is pretty large compared to some of the gains that we saw going from like MMP to RHIP. Now, I will also notice that the data quality issues that I'm talking about here are with the features and not with the labels, so not with the demonstrations. So we're able to make these type of quantitative claims. But later, I am going to talk a little bit about issues with actual labels, which is a much harder problem to quantify what's the right thing to do. So the third lesson, and I think that this was the most bitter lesson for me, was that skew between offline and online systems can have a massive impact on your experimental results. Martin Zinkovich has this great section on training serving skew in his Rules of ML article that I definitely recommend reading. It's pretty short, but I think really good for ML practitioners. And we had a few sources of skew in our experiments. For example, with the metrics, that did introduce skew. And we knew we had tried to address as many as we can, but some of them were just not addressable. So for example, it's like some metrics like customer satisfaction surveys, that's actually kind of what we care about the most. Like, can we improve CSAT scores? Those can only be measured online. And we have to hope that by improving some of these offline metrics like route conformance that we can measure offline, that will actually lead to better customer satisfaction. But there is that inherent assumption across these metrics. Second, I think someone asked a question about the ETA estimates, how they change over time. Due to complexity of the logging system, so we actually had to use static ETA estimates, unfortunately, when we were training inverse RL models, even though at deployment time they were using dynamic ETAs. So this is not actually an issue with the inverse RL method at all. We could have just plugged in features for each of these examples that were dynamic. It actually would have been very little change in the ML system. But it's more of a limitation of the logging system, that logging historical traffic at every single past instance or even at some interval just wasn't available to us at the time, unfortunately. And that was definitely a big source of skew in this problem and something that we really thought impacted our results. And then lastly, and perhaps the most challenging, is that our data consists of tracks from actual users in Google Maps. And determining what the right set of demonstrations to train on is a really hard problem. Users are strongly biased towards the recommended route. And when they detour is because we think that the new route is better, or were they simply made a mistake and missed a turn, for example. So we did a lot of things to address this. For example, we only looked at users who were local experts who navigated a lot in a particular city. We filtered out demonstrations where the user, for example, looped back onto their original route. We tried to downweight routes with perfect compliance because we knew there was some type of bias, and we had some very heuristic process for trying to estimate what the strength of that bias was towards the production system. And this was an admittedly ad hoc process because, like I said, this is bias or noise on top of your label. And so there's hard to know for sure what the right thing to do here is. I really do wish that there was a principled approach to this problem, but I think the bitter lesson is that maybe there's not a principled way to address this problem. OK, so then the fourth and then the final lesson here is that in the routing context, you should learn rewards and not directly learn a policy or Q function or value function. The reason for this is subtle, but it's really important to understand why inverse RL is a great approach to this problem, unlike something like behavior cloning. So I glossed over this detail earlier that the destination is zero-cost, self-absorbing state. This implies that actually every destination induces a slightly different MDP in your graph. And you need to be able to efficiently transfer across these MDPs. Right? So basically, yeah, because the destination is a fixed modification of this graph, it just makes it self-absorbing and zero reward just at the destination, and every destination induces a slightly different MDP. So approaches that directly learn a reward function, so this includes maxent, it includes RHIP, require order SA parameters in the tabular setting. Basically, you need to learn a parameter for every single state action pair in your graph. And you're able to transfer across these MDPs completely for free because the destination is just a known fixed modification of this reward function. That's a really good benefit of inverse RL. You also get the added benefit of being able to pre-compute rewards across the entire graph. And then at inference time, you can actually just use a fast online graph search algorithm like Dijkstra or A*, and you don't have to take some deeply parameterized policy or Q function and be doing that with billions of users' requests online, which is super expensive and high latency compared to running Dijkstra. So we got to leverage a lot of that great planning work and ML kind of in a nice we blended them really nicely, I think, here. This is in contrast to approaches that learn a Q function or a policy, where you actually need order S squared A parameters. So you actually need you have an extra factor of S, because you actually now need to learn an extra parameter for every single possible destination. And this gives you, the number of destinations is the number of states, so that's a factor of S. And so intuitively, though, why this is a bad idea is that you now have to learn not only what humans' preferences are, i.e. the reward function, but you also actually have to learn how to get to a destination, even though we already have great planning methods for being able to get to destinations. So why relearn that when we can just leverage that in the actual ML method itself? So to summarize the key takeaways here, so we can use really smart geographic parallelization and sharding and graph compression to scale any inverse RL method to planetary size MDPs. We introduced a couple new methods, including maxent++ that provides some strict improvements over the original maxent by viewing the problem as power iteration. And then the third one is that RHIP generalizes and enables interpolating between many of these classic inverse RL methods and actually outperforms all of them in practice on this very large-scale benchmark study that we did. And after years of working on this problem, we had some of these very practical and simple lessons, I think, that stood out to us as being important when you're trying to apply these in the real world, is that to visualize your predictions, deal with poor quality data, pay attention to offline and offline versus online skew, and then learn rewards and not Q functions or policies. At least in the routing context, I don't think that this lesson applies to all problems, but at least in routing, I think it is a good lesson to take home. So this is a really fun project to work on. It was also a lot about organizational challenges and things like that, which I can talk to you about some other time, but that's a whole other aspect of it too. So thanks everyone for listening. If you want to learn more, we do have a paper that's appearing at iClear this year in a couple months. It is already available publicly, you can read. And with that, I think we'll move to the Q&A portion of the talk.